Thank you so much for the organizers and for the invitation. It's really a wonderful conference. I'm very excited for the day. And I have to also thank Chadong for giving already such a good introduction to more heterostructures. So you may have life much easier. So from this talk, you learn a few important things, such as the magnetization that comes about because of this moire heterostructures, the Chern number that appears has immense consequences on the related physics of the system. And what I want to convince with this talk is that, in fact, even the monolayer geometry, so the very curvature of each monolayer of a PMD, even before having any moire, actually has quite important consequences, particularly when we're talking about how robust these bands are when we put disorder in the. Okay? So, we've come a long way since the first proposal that quantum Hall could be realized on the lattice without any magnetic field. Since 2013, we've been seeing quantum anomalous Hall effects on many materials and many more heterostructures. So it became just a reality that you can have quantum anomalous Hall without any magnetic field. And it is a very natural question to ask. Okay, so when we have strong interactions, then we also see fractional Chern insulators, fractional anomalous Hall. And a decade ago, this was proposed because this is a very natural extension of the Haldane model. And usually in all of these proposals, it's a little bit intricate how you actually could get such fractionalized expectations on a lattice. But what we've been seeing in the last few years is that these two-dimensional materials, two-dimensional heterostructures provide us like a whole new playground of different systems where we can correlate phenomena because of very narrow bands. So we've been steadily seeing the magnetic field going down from the Young's group first, when the graphene on HBN, Amelia Collins group, where he's seen fractional Chern insulators on the binary graphene. And now, of course, quite amazingly, we have the evidence for fractional quantum anomalous Hall effects with zero field, with absolute zero field in these twisted MO2 homovalents. Okay, so these were the first experiments in which are basically thermodynamic, based on the formula. You know how the gap changes with the magnetic field. You can tell that there's anomalous fractions, fractional anomalous effect. But also in transport, we have seen that these fractions show up, and even in pentalayer graphene now, many different fractions. Okay. So it looks like it's really important to have two ingredients. We need flat bands to have strong interaction, and we need Chern number in order to have topology. And that seems to be the basic ingredients that we need. And what I'm going to try to convince you today is that not all flat bands are really created. And some flat bands are a little bit more stable, more robust than others. And in particular, what chiral Landau levels, which basically appear in anomalous systems like in the Dirac fermion. The zeroth Landau level of the Dirac fermion is really special in terms of Landau level. Okay, so we've all probably at some point solved a Dirac equation under a magnetic field. The Dirac Hamiltonian has this nice block of diagonal structure of the derivative operator. And what does this mean is that it anticommutes with a matrix, in this case, Z. And if it anticommutes with this matrix, it means every single eigenstate of this Hamiltonian should come with a pair of opposite energy. So every Landau level at positive energies has a partner Landau level related by this chiral operator, by this chiral symmetry at negative. But we have a special Landau level. And that special Landau level is basically the Landau level that is exactly at zero energy, which by chiral symmetry will be mapped into itself. What does this mean? It means that this Landau level can be an eigenstate of the chiral symmetry can have a definite chirality. And this is exactly what happens in the Dirac Hamiltonian, for example, in graphene, when we have a magnetic field. One Dirac point, if you look at the zeroth Landau level, that will live on a specific sublattice. So in graphene, basically this chiral operator is just a sublattice of it. So something being of a definite chirality will be means that it lives on a specific sublattice. Okay. And this is chiral. It's also anomalous in the sense that it cannot live on its own. Dirac further cannot live on the lattice on its own. In graphene, this is solved because you have the other value, which will have a zeroth Landau level of an opposite chirality, which lives on the other sublattice. Okay? So there's a really beautiful paper from very long time ago that basically tells us that the number of zero modes of this problem, so the number of states that is exactly on this flat band, is the integral of the total magnetic. This is an index theorem. It comes about because it's a topological index that reflects the anomaly of the Dirac point. But what is really interesting is that it doesn't matter where you put the magnetic field. It doesn't matter if it's homogeneous, it's constant magnetic field. It can be all magnetic fields through a single plaquette. The number of zero modes is given by the total number of flux quantum that you have in Earth. Okay, so it's really what does this mean is that you can make the field completely random, and you still have a Landau level which is perfectly flat and perfectly at zero energy, and it really doesn't care much about any spatially homogeneous magnetic. So one thing we can do to just show that this is true is look at graphene and their magnetic field, and we can do some numerical calculations with this order. Okay, and here I'm showing you, I don't have really a pointer, but what I'm showing you here is at a fixed disorder strength and changing the correlation length of the disorder, which means that if I'm up there, I have a disorder that just mixes within one value, within one Dirac. And what I can see is that a very, very sharp peak for random hopping disorder and random phase disorder. Both of these disorders still keep the Hamiltonian chiral. So there is still chiral symmetry exactly in our problem. So as we see, the higher Landau levels, they broaden with disorder, but the zeroth Landau level remains perfectly sharp, perfectly flat. As I change the correlation length of the disorder, means that I go to the limit of on-site disorder and I can mix the two values. And of course, I can scatter between one to the other, and I will just have broadening of all of the Landau levels in the same way. So that happens very clearly for the hopping disorder, and for the phase disorder, you see everything also washing out. Okay. So how is this important for TMDs at all? Okay. So in TMDs, quite generically in TMDs, we have an accumulation of very phase at each of the values. So these two values are related by time reversal symmetry. So that you have a positive Berry curvature on one value, you have a negative Berry curvature on another. It depends a little bit on which TMD you are looking, which band is actually on top. Is it the valence band? Is it the K value, or is it the gamma value? But if it is the K value, and all of the physics is determined by what's happening at the K value, we really need to consider that there is a large accumulation of Berry flux on the valence band. And so an easy way to account for this Berry curvature on the Landau level problem is basically looking at the gap Dirac cone. So the gap Dirac cone, so you know that in the Dirac cone, you have a delta function, you have high Berry flux localized at divergent at the Dirac point. When you gap it out, this smooths away. So now you have Berry curvature, which means that the wave functions, they kind of wind around. It's not a quantized winding number anymore, but they kind of wind around such that you have an accumulation of Berry. And what happens to the Landau levels of this problem is that they actually look very much like the Landau levels of the Dirac cone. They just got shifted, one up and one down. Why does that make sense? Well, in graphene, this mass term that we are putting, which are basically, it's giving a positive mass to one chirality and a negative mass to the other chirality. So the only thing that we are doing is shifting the energy of where this chiral Landau level is when I shift up and when I shift down. Okay. So nothing really changes, importantly, nothing really changes of the wave function. The wave functions remain basically. So we can ask the same question, what about disorder? What if I put disorder in this problem? And you can see quite nicely that the behavior remains exactly the same. You know, this zero Landau level, this chiral Landau level is immune to any disorder that preserves the chiral symmetry. It remains very, very sharp. Here I'm showing you 3 pictures where I put a larger mass. And one thing that you can even notice is that as the mass becomes larger and larger and larger, it becomes even more protected because you don't have the other guy to scatter to, because you change it with a different energy. Okay, so it's extremely well protected. So now imagine that we just have one band. In the TMDs, we don't really have these Dirac bands that we can keep trace of what is the lowest bands of the Dirac or the highest band. We really just have a quadratic band, quadratic valence band. And I want to ask myself, so is there any effect of the very curvature? Well, if I look at the Landau level spectrum, if I expect a gap Dirac Hamiltonian, I expect my first Landau level to be right glued to the top of the band. While in a quadratic band, in the free fermions, we expect that to be shifted by 1/2 and the Landau levels to be equally spaced. So there should be a way for us to capture this difference just in the low energy theory, in the low energy, the theory of the lowest band. And what we're going to do in order to recover that, we're going to start with a massive Dirac Hamiltonian, and we're going to downfold to the lowest band. We're going to expand second order perturbation theory and see what is the theory for the lowest band. Okay, so that's what I'm doing here in the second line. And I can expand that, including a magnetic field. And what I find is the theory of a quadratic band in the magnetic field. We know very well what are the Landau levels of that theory. Those are just these Landau levels, right? But there's another piece that it's there because of the Berry curve. And that other piece turns out to be the curl of A, so it's proportional to B. And that's nothing but a Zeeman shift that would pull these Landau levels to the top of the band. Okay? So that Zeeman shift, that additional Zeeman shift, what it is, it's like due to the orbital G factor that you have that comes from the Berry curvature on the top of the band. Okay? So if it was really a gapped Dirac cone, simple Dirac cone, we know exactly what G would be. G would be lambda V squared over M, with this lambda being exactly equals to 1. Now, that's not necessarily true in TMDs, where you have quadratic corrections. This is a very, so there's additional corrections that could change that G factor. It could make it larger, it could make it small. But we do know from already quite old experiments on the Landau levels of WSET, for example, that there is clearly a special Landau level. There's clearly a Landau level that has that is the zero that I can associate with the zeroth Landau level, and that depends on which valley. So one of these Landau levels on one valley, it would be connected to the bottom band, and the other one on the other valley would be connected to the top band. And if you change the polarization in this experiment by King Paimak, you would see this special zero Landau level to appear on the other valley. Okay, so we can do some numerical calculations. Put a tight binding model for TMDs under a magnetic field, and I just want to call your attention for what are important Landau levels to keep track of. Basically, each valley, K and K prime, will have an orbital character of d plus id, and one valley d minus id on the other valley, where that's dxy plus idx squared minus y squared. And then you should also have Landau levels from the dz squared orbitals coming from the convection band. And once you put this in a magnetic field, you see that one of the D plus or the D minus, whether the orbital magnetization associated with this orbital is pointing in the same direction of the magnetic field, it will get shifted up, while the other one is going to get shifted down. And you see that in this Zeeman splitting of that specific Landau level. So if we put disorder, if we do exactly the same structure, the same idea, and we just put disorder that preserves chiral symmetry, in this case would be disorder that makes sure the plus and the minus are locally the same. They don't have different potentials, that they're degenerate. So we are talking about disorder in how they pop, but not disorder in the changing the chemical potential of the D plus versus D minus. One thing that we can see very nicely is that if the disorder is non-chiral, all of the Landau levels behave the same. They all get killed, okay? But they all get broadened. But if the disorder is chiral, you see that this protected state that has the chirality that goes along the magnetic field, it stays sharp. Okay. So in the I didn't say that, but even in this theory of this entire theory here, if lambda equals 1, I can tell you that that flat band, if the number of modes in that flat band is protected by the same topological index that is protected in the Dirac model. Okay, so hopefully what I meant to say with all of this is that really not all flat bands are really created equal, and it's really important to consider orbital magnetization to know how stable they are to random. And now what we want to know is, okay, so what about twisted TMDs, which is really what we are talking about. And basically we now are in an era that we have more tuning parameters to make bands flat. So now we have the twist in order to make bands flat. And this is, we know what happens with just Dirac cones under super Moiré potential. This was given by Bistritter and McDonald. This is the Hamiltonian. Everybody probably knows very well by now. But there's a nice limit here where we basically kill AA hopping, and we just have AB hopping. That's called the chiral limit. And in that chiral limit, we will have perfectly flat bands at magic angle. In that limit, this Hamiltonian has chiral symmetry. The bands are perfectly flat, and the two churn bands are living spatially at different sublattices. So they also ideal vortexable. These are other things that are not maybe that important right now. So the connection of this zeroth band to Landau levels is something that people have been exploring quite a bit. So first G1 made this connection to the similarity of the zeroth Landau levels with these wave functions of this band. Then Benoit Estienne and Valentin Raquel, they looked at actually made the exact connection to the bands of the Moiré bands at the chiral limit. They're exactly what the Landau level functions would be if the field would not be uniform. So basically they feel a field which is not uniform, and therefore, and then Viktor Galinsky related this with the topological limit. So like I said to you, the 0.11 doesn't care if the field is not uniform. So when you go and write down the theory of the chiral fermions under the interlayer hoppings, which basically creates some fictitious field, a way of thinking about the magic angle is one in which the effective magnetic field, the magnetic length associated with the effective magnetic field, actually coincides with the Moiré length. So that's a fine-tuned point, but it's a point where you can describe the two theories, where there's a very nice connection between the two theories. So hopefully what I told you is that it is important to consider Berry curvature if we're talking about electrons and their magnetic field. You need to keep the orbital G factor in there. So in order to create a continuum model for the TMDs, which is what I'm interested in this talk, we should keep this additional component. How are we going to do that? Well, we can start with the chiral limit. That's a good starting point. So we start exactly with the model for the TBG. But now we know there's a disbalance between the A and the B sublattice, right? So I just do that. I put in an additional mass that shifts the A sublattice and the B sublattice, and therefore creates a mass gap. And that's maybe a little bit of a silly thing to do. You know, this is basically, you think about, it's very similar to TBG this graphene with aligned with the GPM. You also break that, you create a little mass gap, that will be this mass gap. But what is actually quite insightful is to do the same thing that we do with the magnetic field, which is downfold to the lower bands and see what are the additional corrections to our theory of the TMDs. And what you get is that. So you get basically p square over 2m. So it's a free electron, right? Under a Moiré potential, which has an interlayer Moiré potential, an interlayer coupling. That is exactly the same. These are exactly the same as what Alan MacDonald and Wu found in 2019. But again, there should be this additional component of the Zeeman shift. But now here there's no net magnetic field. So some field magnetic field up, some field magnetic field down. So if we have contribution like that, it should appear both positive and negative. So that's basically a spin-orbit couple. It's not on spin, it's on an isospin, with this case is layer, but what you're going to get is a correction, which is of the same order as all the other terms. There's a layer orbit coupling, and that lambda is tells you like how close to Dirac theory you are. So that's exactly one if you have a gap Dirac. Okay. So in this model, basically, we just have free-fitting parameters, which is how close you are to the magic angle. So that's the alpha that we have also in PVG. How close you are to the chiral limit. That's this beta. If that beta is 0, is exactly the chiral limit. And then we have the extra layer orbit. And just what I want to say also is that if we have beta equals 0, if you have lambda equals 1, this Hamiltonian will have a turn band which is perfectly flat, which is something that you could not possibly do if you didn't have some long range type of openings reproduced like this. Okay? Because any free fermion with any potential would never be perfectly flat. You know, there's a mathematical theorem that guarantees you that that wouldn't happen. So with these are the relationship between the string parameters and the interlayer couplings that appear on the theory. This gives us a very nice rule of thumb. So that at magic angle with this the effective mass, interlayer potential, and interlayer hopping, they satisfy this equality, which you can read as basically interference condition where the kinetic energy times the interlayer energy equals to the hopping energy squared. So it's like an energetic, that the magic angle happens at this energetic balance. And you can take that a little bit beyond its degree of validity, and you can find that based on some DFT parameters that we can expect MOTE2 to have an angle of around 3.2 and WSE2 of around 1.6. And this is the data that we did our DFT fittings. So basically what you see on the top picture is a fit without considering layer orbit coupling, and below is a fit with layer orbit coupling, and you see that we get a much better fit if we just allow for this additional term. And we can also see that beta, so the chiral ratio, is 0.2, 0.4, depends on the actual DFT. But it's smaller than what it is for TBG, which is around 0.8. So you are closer to the matrix, the chiral limit in the TMDs. On top of that, we also see that the layer orbit coupling is around 0.7. So it's actually a quite big number and quite a big correction in the theory. And we should definitely take that into account. So just a little bit of phase space here for MOTE2, which has around theta over theta c like 2.0, at 0.7, that would put us in a different topological phase, which means that you don't need the moiré itself to bring you to the topological phase. You are already in the topological phase. And there's an actual topological phase transition as you turn off that lambda. Okay. So that basically enlarges the topological phase. And it also allows, like I was saying, at lambda equals 1 and beta equals 0, to have the chiral limit where you have perfect ideal bands where you have this the nice relation, this ideal relationship between the trace of the quantum metric for those that are in through this problem to the very curve. So yeah, so that's all I wanted to tell you. Basically, it is important to consider seeing the single layer geometry into the Moiré problem. That geometry will enter if you just have a magnetic field, that geometry will enter in orbital Riemann shifts, but that will be responsible to something like a layer orbit happening in the Moiré problem. And one thing that I think it's kind of beautiful on all of these materials that we have seen, all of these exotic phases, they all happen around the K-value. You always have a lot of geometry around the K-value. And I believe that this additional contribution of the single layer geometry is actually extremely important to stabilize this exotic phase. And yeah, the layer orbit mapping work is done with Valentin Trepel at CCQ and Nicolas Reynaud that was visiting at Columbia for a year. And now this calculations on disorder, this is being done by my student teacher Thing and postdoc. So that, thank you so much for your
Very nice talk. Can you hear me? Okay.
Yes, the speak on.
It's y'all.
So I'm just wondering what are the three parameters in this layer orbit coupling? So that without that, there's the continuum model has parameters that depend on the structure. But now extra there,
right.
Layer orbit. What are the three?
So this is the free parameter that you can fit. The way that basically, if you were to approximate, if you want to think about what this number should be, if you think about approximating the lower band to gapped Dirac band, so no quadratic corrections, that would be lambda equals 1. But then these can get corrected not by the mass, so the mass is irrelevant, but if you then curve up or curve down, that will lead to corrections which make lambda larger than 1 or smaller than 1. But so the fitting parameters that we had before was basically VW, psi. So basically now we have the same number of parameters, which is the alpha, the beta, and the lambda. But now the fit gets a little bit better.
Okay.
We're not overfitting by putting more parameters.
Yeah.
This now all of the V, the W, they all get related to the alpha and the beta and the lambda.
Right. I guess
Lambda equals 1 in our model.
You're fitting them the gap drag.
In a sense, in order to capture the very curvature of the band, yes.
Hi, very nice talk. And I have two questions which are kind of related to what will be presented next. And the first one is, when you showed the slide of Harlow pressure, you said the flat band doesn't care about non-uniformity of the magnetic field, but in a real formulation, I think there should be another external potential that kind of cancels that, and then it makes the band flat.
So the Aronoff pressure is about a spin 1/2 particle in their magnetic field.
Yeah.
So that's the result for a spin 1/2 particle in magnetic field. In the Moiré potential, that spin is not a spin; it's an isospin, which is basically it's like sigma z tau z, where sigma is the sublattice and tau is the layer. So it knows both of layer and sublattice. It will change by changing layer and by changing sublattice. So in that spin, one will feel a spin up, a magnetic field up, and the other one will feel a magnetic field down. So when you want to calculate the index of that, you need to make sure that you are block diagonalizing the right spin and that you are calculating something that does have a finite magnetic field. Because in total there's zero magnetic field, right? There's some reversal symmetry in these.
Okay. Another question is, you added a layer orbital coupling term, so it's kind of equivalent to chiral limit of this binary, but in reality, even if you don't add that term, you also have near ideal quantum geometry.
So-
Can you explain that in your?
Yeah, okay, that's actually a really interesting question, right? So how does it work so well without considering this? What I am saying is that you absolutely need this term to make that perfectly ideal, to make it ideal, to make it perfectly flat. This is necessary. Okay, it's necessary because you cannot put a quadratic band under any potential. You cannot put that. You cannot make a turn band which is perfectly flat. That's a theorem. So you need this term in order to make it perfectly flat. Now, it turns out that you can engineer the other terms independently to make something that is actually quite flat, right? Quite close to flat. So you just have many parameters in the model, basically. But this gives us, I think this gives us some kind of physical intuition why we would even expect to start with such a good, it's not just by luck, not just by the folding. We know that if you fold a band many times, we will have turn bands necessarily, right? At some point. So this gives us an intuition of like why to actually expect the bands to be so flat and to start. But I'm not saying that if you don't tune all of the parameters independently, you cannot find a regime where you wouldn't need to consider this to get a good result. And of course, that has been done, right?